These machines are the workhorses humming away behind just about everything, from the gas in your car to the cool air in your house. They are, quite literally, everywhere.
But look, it's not just about brute force. There's some really elegant physics going on inside. There's a whole thermodynamic cycle at play, turning raw energy into pressure with surprising efficiency. So the big question is, how does it actually work?
All right, let's start with the basics. What exactly is this industrial workhorse, and what does it do?
Okay, so at its heart, the concept is beautifully simple. Think about a bicycle pump. That's pretty much it. You've got a piston moving back and forth inside a cylinder to squeeze a gas. That back and forth movement, that's what reciprocating means. The whole point is to suck in gas at a low pressure and spit it out at a much, much higher pressure.
And that one simple function, well, it has a huge range of applications. We're talking jet engines, the AC system in your house, the power tools buzzing away at an auto shop, and even supercritical processes in oil and gas, like hydrocracking. I mean, their reach is just enormous.
So let's meet the key players in this mechanical dance. You've got the crankshaft. Its job is to turn the spinning motion of a motor into the straight back-and-forth push of the piston. And then you have the intake and outlet valves. Think of them as perfectly timed bouncers at a club, one-way doors that let the gas in and out at exactly the right moment. Okay, so we've met the parts. Now let's dive into the invisible engine inside this thing, the compression cycle. This is where the magic really happens. The whole thing happens in a super fast 4-stroke cycle. So first up is induction. The piston pulls down, sucking in low-pressure gas. Then compression. The piston shoots up, squeezing that gas and jacking up the pressure. Next, discharge. That high-pressure gas gets forced out. And finally, expansion. The piston moves back down and bam, it's ready to start the whole cycle over again in a flash.
And this is where it gets really cool. On the left, you see the physical machine doing its thing. On the right, that's the thermodynamic journey it's taking, all mapped out on what we call a pressure volume, or PV diagram. Every single one of those strokes we just talked about traces a specific path on this graph. It shows us exactly how the gas's pressure and volume are changing. Honestly, this diagram is the secret language for understanding how well a compressor is working.
And that PV diagram isn't just a pretty picture of the cycle. No, it's a tool. It actually lets us measure the work, the raw energy required to get the job done.
It's actually pretty straightforward. See the area inside that loop on the diagram? That area is the work. It's a direct measurement of the energy the compressor has to burn to do its job. So, a bigger area means more wasted energy. And that means the goal for every single engineer designing these things is simple. Make that area as small as you possibly can.
But here's the thing, how you compress the gas really matters. The journey from low pressure to high pressure can follow a few different paths on our diagram. That red line, that's isentropic. It's what happens if the process is so fast that no heat can escape. The green line is isothermal. That's the dream scenario where you keep the temperature perfectly constant. And that blue line, the polytropic path, well, that's the real world. It's always somewhere in between. And this is the key, you have to remember this. That isothermal process, that green line, it creates the absolute smallest area on the PV diagram. And what did we just say the area represents? Work. So less area means less work, less energy. That makes the isothermal path the theoretical gold standard. It's the perfect, most efficient compression possible.
So knowing the perfect way to do it is great, but how do real-world machines stack up? Well, for that, we need to look at the efficiency scorecard.
There are really 3 main grades you can get. First is mechanical efficiency. This basically tells you how much of the power from the motor is actually moving the piston versus how much is just lost to friction. Then you've got isothermal efficiency. This is our reality check. It compares the actual energy we used to that perfect isothermal energy we just talked about. And finally, there's volumetric efficiency. This one measures how good the compressor is at actually filling up its cylinder with fresh gas on every single stroke.
And why does any of this matter? Because bad efficiency has very real, very expensive consequences. We're talking higher electricity bills, more fuel burned, more wear and tear, more repairs. Think about an industrial plant where these things are running 24/7. Shaving off just a few percentage points on the efficiency scale can literally save millions of dollars a year. It's a huge deal.
So what's one of the biggest enemies of efficiency? It's something called clearance volume. See, for mechanical safety, the piston can't slam right into the top of the cylinder. There's always a tiny little gap left over. The problem is, that gap traps a little bit of high-pressure gas at the end of the stroke. And on the next cycle, that trapped gas has to expand back out before any new gas can come in. It's like having a sponge at the top of the cylinder that steals a bit of your space on every single pump.
Okay, so we've got these pesky limitations like heat buildup and clearance volume. So how do engineers get to really, really high pressures without wasting a ton of energy? The answer is a brilliant strategy: multi-stage compression.
Right, so here's the core problem. If you try to do all the compression in one single go, one big squeeze, it's just wildly inefficient. The gas gets incredibly hot, and hot gas fights back. It pushes against the piston, making the compressor work way harder than it needs to. The bench press analogy is perfect. It's like trying to lift a 400-pound weight in one explosive movement instead of breaking it down. So here's the solution. Instead of one giant cylinder, you use 2 or more smaller ones in a series. You compress the gas a little bit in the first stage. Then, and this is the critical part, you send it through an intercooler, which is basically a radiator that strips out all that heat. Then you take that now cool, now denser gas and feed it into the second stage to squeeze it even more. And let's go back to our PV diagram to see the payoff. Look at that. That shaded area between the two curves? That is pure, unadulterated energy savings. It's work the compressor didn't have to do, all because we took a timeout to cool the gas. By doing that, we bring the actual compression path way closer to that perfect, ideal isothermal line. It is a massive win for efficiency.
And you know, this technology has been getting better and better for over a century. From the first compressors back in the 20s making fertilizer, all the way to the absolutely gigantic units you see on offshore platforms today, the story has always been the same. Push for higher pressures, make them more reliable, and above all else, squeeze out every last drop of efficiency.
So you see, multi-stage compression isn't just some fancy add-on, it's a fundamental change in strategy. It's about recognizing that heat is the enemy of efficiency, and then tackling that enemy head-on, step by step. And by doing that, engineers can reach pressures and efficiencies that would be completely impossible in a single stage. So from a simple piston and a cylinder to these incredibly complex multi-stage systems, the reciprocating compressor really is a marvel of engineering. But you have to wonder, as our world demands more and more efficiency, as energy costs keep rising, what's next? What will the next leap forward in compression technology actually look like?